All right, everyone, welcome to the Olympiad Astronomy live stream for the Astronomy 2020-2021 online Science Olympiad season. My name's Cruz Soto. I'm from the Massachusetts Institute of Technology, currently a freshman studying aero, astro, and physics. And I'm joined by...
Hi, I'm Jeff Shear, and I work at the NASA Johnson Space Center. And before I graduated from Columbia, and I did a lot of astronomy as well. So yeah. So let's start with this live stream. Just a little presentation I made just on the general overview of the event, so you have a better idea of what to expect. So this is I didn't share. My bad. I don't think it makes much of a difference, but
still, you are screen sharing. You need to hit present, I think you mean.
Thank you for that. Even software engineers can have moments. So
that's good to know. That gives me a bit of optimism for my future.
Yeah. There we go. Perfect. All right. So these are just the general topics that you should learn to expect. First, resources allowed. This is one of the few events in Science Olympiad which I thoroughly enjoy, where you can get a laptop. You can get a laptop per person. I guess it's online anyway, but yeah, you get online. Sorry, not online. You get the laptop information. You could also get a binder, which is up to you. I like laptops more because they're more, obviously you get more information, but if you like organization, binders might be the way to go. So it's up to you. There's not really any one-way ticket to decide which one is which. Binder information can be of any size or from any source, as long as it's attached using the available rings. You can use sheet protectors and laminated sheets, so if you like to keep it protected. You also get calculators as well, which will be useful later on. So one of the main topics in astronomy is stellar evolution, just talking about the general stages of a star like our sun, or a star like Betelgeuse, which is much more massive than our own star, or like a star like Sirius, which is or the smaller Sirius, the Sirius that's much less in mass. So it consists of three main portions: the PreMain sequence, the main sequence, and the PostMain sequence. The fate of the star depends a lot on the initial mass of the star. So it'll make a big difference about whether you're very high, like 8 to 10 solar masses, compared to if you have the mass of the sun. So this is a nice graphic that kind of gives you a general overview of the various stages. So you see right above here, you have the supernova, and then down at the bottom, you don't have the supernova. So that kind of shows the differences depending on how massive it is of the stages in the future. So before the main sequence, you have a bunch of gas and dust that's in a dust cloud, and they'll kind of just join together loosely, and then kind of disturbances happen that allow dust and gas to collapse into stars, and then you get the main sequence. So some things, T-Toy is just one of the pre-main sequence stages. Herbig-Hera objects, protostars, which again are just the general stage of the developing stars that's starting to form. It's very chaotic at first, and a lot of the pre-main sequence is when you're trying to stabilize into the star that we know and love to study. And the gene's mass is the minimum amount of mass that you need clumped inside of the cloud in order for it to for gas to start fusing together and start forming protostar. So there is, on the upper left, you have the HR diagram with the path of a pre-main sequence stars as it's heading towards the ZAMS, which is called the zero age main sequence, which is basically at what point does this start forming on the main sequence. And then below you have it's kind of like a graphic of how pre-main sequence stellar evolution occurs. Main sequence is where most of the star has its lifetime, about 90%. This is where you get, the majority of stars out there. The lifetime is proportional to mass. So what that means is that the more massive it is, the less it'll survive. So a star like Rigel, which is like 5 solar masses, I would guess, is going to last a lot less than a star like our sun. And our sun will last a lot less than a star like Barnard star, which is very, very small in its mass compared to the sun. On the upper left is a general idea of the structure of a star's atmosphere. So you see it as a convective core and as a radiative envelope. And then at the bottom, you have the Husband-Russell diagram with the main sequence as shown here. So the Sun, Spica, Proxima Centauri. The PostMain sequence is the point at which a star normally fuses hydrogen to helium. After a while, it's going to lose its ability to fuse hydrogen to helium because there's not any left. And so it's going to start contracting. And after a certain point, it's going to contract enough to fuse helium into carbon. And then after that point, this is where the mass makes a difference, because if it's a star like our sun, it just will decide to just shed its layers into a planetary nebula. And I realized I forgot to add that, so apologies for that. But if it's a star that's much higher than, let's say, 2 to 5, much higher than, let's say, two solar masses, then it's going to go kind of into a runaway effect in terms of fusing elements into a new element. So it's going to go into silicon, magnesium, carbon, oxygen, all the way into iron. Now, the big thing about iron is that it cannot generate energy through fusion or fission. And therefore, after a while, the star just becomes inert. And after a while, it just clumps enough until there isn't enough energy for the star to be stable. The star collapses on itself, and this is where you get the supernova. So things like the Crab Nebula. Oh wait, no, that's type 1a. Sorry, is the Crab Nebula type 1a or type 2? I forget.
I'm pretty sure it's type 1a.
Okay.
It's well, we can pass it. We can pass on that.
but yeah. So you see neutron stars. Neutron star is the post-main sequence part of a massive star. Those are they're very, very dense. And there are very types of neutron stars. Pulse stars, as you can imagine, they pulse with a certain period. So it'll go like beep, 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 every with a certain regularity. Magnetars are pulsars, except they spin really rapidly. And what this allows it to do is it create very strong magnetic fields. And then you have blazars, which I forget. Do you remember what they're known for again?
I'm pretty sure blazars, and actually you were correct about, I'll go ahead and correct that it is in fact a type 2 supernova. I looked it up. Blazars are generally known for, if I'm correct, blazars are known for, I think they're characterized by having a jet, the electromagnetic radiation in one direction. Generally, it's just a pulsar that's pointed towards the observer, or towards, in our case, it's the Earth, if I'm correct. Yeah, so for a good example of a blazar was the blazar that it should be on your list, that was used to discover the sculpture wall, where we have about 1/3 of our baryonic matter in the universe stored. That's a very prominent example that you may need to know for the competition.
Yes, thanks for that. Yes. And then if it goes far enough in the mass of the star, it can go even further than that, and it can create a black hole, which of course you probably know about, that the star, that light from a black hole cannot escape. It is dense enough that it forms a singularity at the very, very bottom. The short star radius is the radius at which you have the event horizon, which is the point of no return. So if you think like in Interstellar, when you have, the spaceship going into the black hole, obviously they kind of don't want to go inside, so they kind of push back as hard as they can. That's kind of the idea of what it would be like to go into a black hole, which obviously you wouldn't want to do. But Hawking radiation is a cool feature where you have an antiparticle and a particle. And what happens basically is that it kind of spontaneously forms. And then because of the black hole, the particle spits out and the antiparticle goes in. And the no-hair theorem is a theorem in which you can describe a black hole through 3 parameters: electric charge, angular momentum, and mass. So that could come up as well.
Yeah, and if I could interject before you go to the next slide, I'd highly recommend, if you are going into this event, something that helped me after, not while I was actually competing, but something that I could see helping students, is reading A Brief History of Time or A Briefer History of Time by Stephen Hawking, where he talks a bit about Hawking radiation. And essentially what it is, it's a derivation of Maxwell's equations and Einstein's theories of relativity that basically states that time is relative. Time is not an absolute like we think of in Newtonian mechanics. And the cool thing about that is that because time functions in that way, a particle moving forward in time is the same as an antiparticle moving backwards in time, which essentially means that justifies Hawking radiation, which means that when a particle goes in, as Jeff said, an antiparticle has to come out. So lots of cool facts like that are discussed in that book, and will definitely help you with the more conceptual parts of this test, which I think will come up a bit more, considering we have to ask you guys harder questions since you have access to the internet.
Yes, that I can attest to that. That is a really cool book that I've read before, and it is awesome. So, yeah. All right. So galaxies is another main part, at least for this year. So as you know, galaxies have three main parts: the disk, the bulge, and the halo. The halo contains the majority of dark matter, also some globular clusters as well. The disk is the majority of stellar formation. So this is where you have your this is where you have your spiral arms in a spiral galaxy. This is where our own solar system is. The bulge is near the center. It's surrounding the supermassive black hole at the galaxy center. And this is where you get a lot of the dust and gas. The Hubble diagram is used to characterize galaxies. So if you see here, there's like a little fork. So you have ellipticals on the left side, and then you have spirals on the right side. Elliptical galaxies are older galaxies. You get them from spiral galaxies. Spiral galaxies will evolve to become elliptical galaxies. Elliptical galaxies are kind of like a circle. They're a lot older. Star formation doesn't really happen a lot in elliptical galaxies. Spiral does, and then regular kind of just a weird shape. It's really hard to explain, which is why they're called irregular. So yeah, there are some examples of elliptical, spiral, and irregular galaxies. So the math, yes, this is the portion that everyone.
Oh boy.
I remember as yes, I remember as a competitor. Yeah, it was an experience, and every time people talk about astronomy, like I don't like the math, and you're not wrong on that. But it's actually, I mean, I don't think it's that bad, but that just comes with a lot of practice. I think a lot of this, a lot
Could
of the
be worse.
yeah, a lot of the math part, you just have to like practice. And something to know about it is absolute apparent magnitude. Just very quickly, apparent magnitude is when you look at the night sky and it's literally how bright it is. So Hipparchus made a scale like in the first century BC where he realized that the brighter you are, there's like a certain scale, it scales. So he made it so that a star with an apparent magnitude of 1 would be 100 times brighter than a star with an apparent magnitude of 6. So that means it's about 2.54 times. So if you go up 1, then it's going to be 2.54 times brighter than that. And the absolute magnitude is the apparent magnitude if you took the star and you put it all at 10 parsecs. So what's neat about that is that you can use these two quantities to create a distance modulus. And brightness is flux is sort of the same thing. Brightness is analogous to magnitude. Excuse me. Flux is brightness, except it's per unit area. But in effect, you can kind of make them analogous to each other. It just depends on which portion you are putting the unit in. So whether it's unit area, or you can do a radiance, which is per unit wavelength. But they're all interchangeable with each other, more or less.
Yeah, all generally related by square modulus. So generally the farther away you get, you have the same brightness or the same amount of photons per unit area squared. So for example, if you double your distance, you're going to quadruple the area in which those photons are scattered.
Yes. And the main part of the math when it comes, or one of the main portions of the math is distance calculations. So you have this concept called the cosmic distance ladder. And an example, I guess it's not so much a ladder, for the upper right-hand portion. Kind of the idea that as you go further away from Earth, you kind of change the methods that you use. So the closer you are will be much different than further away. The first one is parallax. So one thing that you can use to kind of see this notion in effect is if you take your finger and you cover your left eye. I'm sorry. Well, I guess I'm covering my right. Cover your right eye, and then cover your left eye. Now notice that the finger will move. The idea of it is that you have the sun and the Earth, and that as the Earth is rotating around the sun, the star in question will move as well. And then you can do trigonometry. You can like this. Like if you see my elbows is the Earth, and then my fists are the star, and that you have like the angle there. And you can find that distance through doing d, which is the distance in parsecs, equal to 1 over the angular the angle that I mentioned in arcseconds. A spectroscopic parallax is using the absolute magnitude, which you can find through using the HR diagram. So the HR diagram allows you to, assuming it's a main sequence star, if it's a giant or supergiant star, you cannot use spectroscopic parallax as much. Theoretically, you could, but it's a lot easier when you're doing it on the main sequence. What you can do is, actually, I'll go back to make it easier. The HR diagram, you see this, CC. So if you have a star, let's say it's Series A, and I'll annotate if I can. So it's like, if you have it right here, right? What you can do is you can notice, oh, I have an apparent magnitude of absolute magnitude of about 2, right? And it's pretty straightforward to calculate. Let me annotate out. It's pretty straightforward to figure out the apparent magnitude. You should go outside and just measure it, right? The absolute magnitude is the harder part, because you have to try to figure out what the properties of the stars of the star are, and then from there use the distance modulus to find out what your distance is. What's cool about Cepheid variable, so that's a little further away than parallax. Further than that, Cepheid variable stars are what's called standard candles, and what's useful about that is that so they pulsate with a certain period, and this period is called the period luminosity relation. And what that basically means is that if you calculate the period using the light curve, you can figure out how long it takes from one point and then up and then back again. So let's say it's like 5 days, let's say. And from that, you can use, there's like a formula that you can use where you can figure out its luminosity, and from earlier, its apparent magnitude. You can actually find the apparent magnitude just from the light curve itself using the median. And then from those, use those two values, distance modulus. So that's what's really cool about these standard candles. Same vein as type 1a supernovae. So type 1a supernovae are when a white dwarf is too massive, that it basically just explodes. And what's cool about that is that it has the same absolute magnitude all the time, because it has the same mass at the Chandrasekhar mass. So it's kind of the same thing, that the absolute magnitude no matter what, and you can calculate its apparent magnitude to find the distance. The Tully-Fisher relation and the Fabry-Jackson relation have to do with the rotational velocity of the galaxy. Tully-Fisher is for spiral galaxies. Fabry-Jackson is for elliptical galaxies. And finally, Hubble's law allows you to calculate the redshift, which is basically the idea that you have your waves, and then as the star is going away from it, the waves stretch, they become more red, and vice versa, coming towards becomes more blue. And from there, you can calculate the recessional velocity, basically the how fast the star is moving away from Earth, and you can use that to calculate, using Hubble's law, how far away the star. Usually for galaxies, stars is very unlikely that you're going to be able to find the exact redshift of that, but for galaxies, it's used a lot. So yeah, cosmology is the evolution of the universe. This is a relatively new topic. The Big Bang, which you probably know if you have not watched. Well, I was going to joke if you watched the Big Bang Theory. But Big Bang is when it all started, singularity, and kind of just, right? And then the gut, which is a grand unified theory, is the idea that all the forces in the universe kind of came together at the very beginning. And as the universe cooled, the forces separated. So you have the electromagnetic force, you have the strong force, you have the weak force, and you have the gravity force, and they are kind of all together. And as it's cooled, the forces separating each other. Inflation is the idea that the universe rapidly expanded. So kind of just a little bit, and then boom, it became much bigger, much faster. This cosmic microwave background radiation is the furthest that we can see through light. And the idea behind that is that you have in the early universe, it became way too hot. So all these electrons were kind of going back and forth and, kind of swimming around, and the photons were crashing into electrons. As soon as it became cool enough for the electrons to become the electrons in the atom that we all know about, the photons stop crashing into electrons, and that's where you see in the upper right hand corner the CMBR. And then right after that, stars then form, which is called the Dark Ages. This is the period of time right after the CMBR formed. In the universe, there are not just matter that we're made of. There's also something called dark matter and dark energy. Dark matter solved the problem where the galaxies would basically be rotating too fast through angular momentum, the conservation of angular momentum, and it should rip apart. Basically, you have a flattening rotation curve where the rotation, normally through angular momentum, the rotation curve would dip down, but we saw measurements where it just kind of just flatlined, and there had to be a mass somewhere, and that is dark matter. And we don't know exactly. We can only detect dark matter through gravitational interactions. And some theories of what we think are dark matter are WIMPs and machos. Dark energy solves a problem about the accelerated expansion of the universe, in which we basically realized that normally it was before like 1998, we thought, oh, it's just expanding normally, a flat rate. But then we realized, wait a second, it's actually accelerating, and there had to be some sort of energy, some sort of thing out there that caused that. And that's dark energy. We don't really know what it's made of yet. that's kind of the one big question of cosmology, is what exactly is dark matter and dark energy. Still figuring that out. And the big questions, the big thing that this helps determine is basically what will our universe become. There are three main fates. One is that it could just coast like normal, just kind of just chugging along, not much is happening. It's accelerating just a little bit, but kind of just coasts. The second thing is it could go haywire, basically. Dark energy will become so much that it basically rips apart the atoms from each other, which, as you can imagine, is kind of painful. And it's got the big rip, in which space-time itself kind of just literally rips. Finally, you have the third solution, which is matter becomes so concentrated, becomes so much that it sort of like stops moving, expanding, and then it crunches. It's called the big crunch. And then another theory suggests that it could go cyclical motion, in which you have another big bang and the big crunch. But these are all theories at the point. But it could come up. So, lower right is just a general idea of all the stages of the early universe. So some diagrams, some general diagrams that you could come across. The Edgeworth diagram, as I mentioned, categorizes stars based on their temperature. It could be temperatures or color index B minus R, B minus I. All it does is basically you have the light from a star and has certain filters which separates depending on certain wavelengths. So B is blue, I is infrared, V is UV is ultraviolet. You could use the subtraction of that. It correlates with temperature. The right side, it could be luminosity. It could be absolute magnitude. You also have black body radiation, which the idea is that you have a star that perfectly absorbs and then emits energy, and that's the black body radiation. So you have the curve of Planck's law, which is the idea that you can measure how much energy a star has through calculating the area under the curve here. So I'm going to annotate as well, right here. So all this area under here, that's Planck's law. You also have Wien's law, which says that if you know the peak of this curve here, then you can calculate the temperature of the star. And Planck's law was made to solve a problem called the ultraviolet catastrophe. Well, the classical theories you see here is fine in long wavelengths, but then it kind of goes haywire. It goes to infinity, which is a problem. So that's what Planck's law was used to solve. So some tips and tricks in general. As I mentioned, organize your Binder laptop, use folders, make sure you can actually find all the information that's in your resources. Practice, especially with the math stuff. It can be tricky sometimes to figure out exactly what equation to use and how. It's important. Like I mentioned earlier, some of them, like with the galaxy part, like they just because you have the rotation doesn't necessarily mean it's gonna be the same equation every time. And even I should add for the Tully-Fisher relation, it's also technically changes depending on what wavelength of light you use. So that's also Tully-Fisher actually is a very annoying relation to deal with. And finally, work with your partner to divide up study and efforts. It's kind of just general science Olympiad tools, tips in general. So some resources, Chandra is a great resource, especially for deep sky objects. They have basically for like, I can't even tell you how many objects they have. Hubble is a great site. Astronomy Picture of the Day is a great place for deep sky objects. AstronomyNotes.com is a great online textbook that goes into like cellular evolution and brightness and stuff like that. Galaxies, very in depth. Finally, if you can, Carol Osley's An Introduction to Modern Astrophysics. The math can be tough at times, but the subject material in general is quite detailed. And Barbara Ryden's Cosmology, that's a great resource as well. Great, yeah.
All right, so I'm assuming everyone's just kind of thinking, all right, we're all done, but actually, I actually do have a portion of the presentation I'm going to do. So I'm going to go ahead and share my screen now. All right, so the thing is when I went into astronomy, I think this is sort of a disambiguation of one of my greatest tips, which is the idea that we should not be here, we should be up here, which is not really visualizing problems. And I think visualizing a lot of these problems as opposed to just memorizing math really is a really huge help in contextualizing the things that you have to deal with. So what I'm going to be doing here is we have 4 problems. This one that I implemented is actually a problem later on. This is actually a 7-part problem, but given the time scale that we have, I don't think I have enough time to talk about 7 parts. So I narrowed it up to the 4 most important ones and the 4 that are easiest to talk about. So this is an excerpt from the UT Invitational from last year. And so I wanted to talk about, so just some basic ideas behind how you would tackle a problem like this, and without just doing the math. And I think that it's important to know where a lot of this stuff comes from, specifically because to make things harder for this academic season, there has to be competition season, there has to be a lot more critical thinking involved. And as such, instead of just asking you guys to identify things that some cheaters, not necessarily saying that anyone's a cheater, but there's a possibility of cheaters reverse image searching or just finding on the internet, we need to ask you a bit more contextually gripping problems. So for example, instead of asking you what is the, what is 1 parsec in meters, we might ask, how would you derive the definition of a parsec? How would you derive the definition of a parsec in terms of astronomical units? How would you define it in meters? And what is the process for that? How would you define it? And so we ask you not necessarily questions, but questions about the questions that we might ask you. And I'll explain right now. So let's start off with part A. So how far away is this star from Earth in parsecs? So a star has a parallax angle of 0.0111 arcseconds. When viewed from Earth over the past 5 years, its position in the sky has changed by 0.10 arcseconds. All right, so how far away is this star from Earth in parsecs? So normally what I would do is just sort of do the math and go from there. And as many of you might know, the distance to a star in parsecs can just simply be derived from 1 over the parallax angle. So 1 over 0.11. And that would be the distance in parsecs, and that will more or less give you your answer. So if we average that out, that's going to be about 1 over 0.01. And if you do the math pretty quick, that's going to be about 100. If you do this math exactly, it's going to actually be 90 parsecs. because I've done the math earlier. But the question really is, where does this come from? And that's what I wanted to talk about today, because we might ask you questions. So what defines one arcsecond? What defines this relationship? And so the definition of a parsec is what I wanted to touch on. So a parsec is defined as the distance of a star from our star system that would have a parallax angle of 1 arcsecond. So I've drawn this diagram here. So when we have stars at a certain distance from us, we have a lot of assumptions we can make. So the first assumption I'm going to say is that for any given star in the universe, I can draw this diagram. So as you can see, this is star over here I'll call B, and this star over here is the sun. This star, now normally blue stars are very large. You usually have blue giants, won't really have small stars like that. Let's say that this is a white dwarf or something of the like that just so happens that I drew it blue. But this obviously isn't made to scale. So let's say we have this star B at a certain distance from the sun that we'll define as D, capital D. And at this angle, most people would say theta. I'm going to define this as phi because I'm very quirky, and actually we'll be talking about multiple angles in this example. So this is essentially saying that if I have a theoretical star where phi is equal to 1 arcsecond, then this distance D is going to be defined as 1 parsec. And so just to clarify, I'm going to define what 1 arcsecond is again, because I don't want to take anything for granted. And as many of you might have already known, if I am standing somewhere on this earth, I can see probably about a hemisphere worth of stars, worth of the night sky. There's a reason I can't see the constellation Tucana in the northern hemisphere. That's because I'm in the northern hemisphere, and that's something that you'd see in the southern hemisphere, for example. So I can only see about half of the sky. And the way astronomers divvy this up is like a circle. You know, they have polar coordinates. So as you can see here in this top circle here, I would be able to, from this midpoint that I'm at, see 360 degrees of the sky. But there's just so much out there. If I were to take just a small sliver, you know, if I were to take a sliver of the sky, that's the thickness of this line, and maybe only about a meter of the night sky that I see, I could probably find about 1 billion different deep sky objects out there. So it's a very, very large universe. So we simply can't say, all right, let's do this in degrees. We actually have to break this up into smaller units. So as you probably already know, 1 arc minute is simply 1/60th of a degree. So 1 degree divided by 60 is equal to 1 arc min. And you can probably see where this is going. 1 arcsecond is equal, and that's defined by this tally mark. This is not inches and feet. I know that this is the same nomenclature as that, so I wanted to clarify that. But 1 arc minute divided by 60 is equal to 1 arcsecond. So we're able to divide all of these 60 degrees of the night sky. We can divide them up into 3,600 different parts between arc minutes and arc seconds, because you have 3,600 arc seconds in 1 degree. So that's very useful. So that's what we're talking about up here. So theoretically, if we had one degree here, 1 arc second of vision from this planet, then this would define a parsec. And that's where we get that definition from. And so what this problem is saying, well, if this angle here is 0.0111, then what is our distance? Well, the thing is that we can define this using basic trigonometry. And we could say, all right, that 1 astronomical unit divided by the by d, this distance d, is equal to the tangent of phi. This is just basic trigonometry. So in turn, then we can switch this up and say that d is equal to 1 over the tangent of phi. And the cool thing about this is, well, when you have a sufficiently small angle, you could simply generalize this as saying 1 over phi is equal to d, because this is quite literally 1/3,600, less than 1/3,600 of a degree, which is very small. Anything under 15 degrees falls under what we engineers call the small angle theorem, which is basically saying that sine or tan of theta or phi is equal approximately to phi or theta. So we can make that generalization, and that's where this equation comes from. So one of the things that we might ask you in the competition is to derive this equation. Where does this equation come from? Why does that exist? And that's where you would pull it from. Another thing that we might ask you is, can you derive the standard definition of a parsec in meters without using Google, without using the standard definition by just looking it up? And you would have to derive that. And you would do it using this definition. And I'm going to go ahead and explain that in a second here. So here I have a few standard measurements. And I can see that this is the standard definition for 1 astronomical unit. And I can define this using the speed of light. That's a whole different ballgame that we can talk about another day. If I were to go through and define everything in the universe is essentially based on the idea of what we have behind the kilometer, behind the definition of the meter, the definition of the kilogram, and the definition of the second. All other units, more or less, are derived from there, as well as the speed of light. And Planck's constant. So we have a lot of different stuff that's derived from all of these simple units. So I could spend a very long time talking about how you would derive what 1 astronomical unit is. But let's say if we're given 1 astronomical unit, how would we define 1 parsec? Well, a cool thing that we can do is, if I scroll back up here and give myself some space, we know that 1 astronomical unit divided by the tan of phi is equal to 1 parsec. So if we wanted to define this in meters, well, what we would do is, we know this is in arc seconds, and we know this is, and we could define this in meters. So if we wanted to define this 1 parsec in terms of meters, well, all we need to do is substitute this in. You know that 1.496 times 10 to the power of 11 meters is equal to 1 AU. We go ahead and divide this here. We know that tan of phi is actually unitless. Phi is should be in degrees, but tan itself is unitless. So we would actually end up with this being a tan of 1 over 3,600, because remember, it's 1 arc second, and 1 arc second is 1/3600th of a degree. So we'd have that, and that would be defined as 1 parsec. And what you essentially get is that that 206,265 AU is equal to 1 parsec. That ends up being your answer. If you just solve this math here, that would take quite a bit, and I don't feel like doing it. And you could probably do it at home if you have a calculator. And that's very useful. So that's an example of a question that I've seen a few people throw around, not necessarily the exact question, but an example of something that we might want to ask you: how to derive these units. How do you get this stuff? Because this is stuff that can't just be Googled. It's a lot faster to just do it than spend about 20 minutes trying to figure out where this would come from. And so it's very important that you understand where a lot of the math that you use in this competition comes from. And that's how you would get this simple equation that gets you 90 parsecs. And this is a difference between a question that we would ask you last year as opposed to a question that we would ask you this year via something like Olympiad or Canvas. So that would be the answer to part A. Now, part B, what is the proper motion of the star in arc seconds per year? Well, over the past 5 years, its position in the sky has changed by 0.1 arc seconds. Now, some of you, again, might just memorize the math and say, all right, well, if it's over the course of 5 years, 0.10 arc seconds, we are going to go ahead and divide that by 5 because it's 5 years, and that's going to give us 0.02 arc seconds per year, which is absolutely right. That's the correct answer. Congratulations. So that's the correct answer. But I want to visualize this so that we understand what this means. So what does it mean for the position of the sky to have changed by 0.10 arc second? Well, like I said, let's say we have this planet, sorry, the star, not this planet. See, we have the star over here. At some what we say here, what we can say here is, sorry, I can go ahead and delete these. The cool thing about this assumption here that we can make this triangle is that at any point during the year, if I have my star over here, at some point, the Earth is going to form a line with the sun that is perpendicular to this. And we can define that relationship that we had last time. So what this is essentially saying is that this star has been moved a certain distance. And I'm going to go back and undo all the stuff that I did so I can do this. So we moved this, and this is actually moved up a certain distance. It's moved up an angle. So how are we going to define that angle? Well, I'm just going to go here. I'm going to select this stuff, and I'm going to turn it a bit. Oop, didn't mean to turn this stuff up here, but whatever. All right. And now, cool thing is, this is a 90-degree angle. This is the distance that we're talking about. This is the angle right here. This angle here, which I'll call theta, this angle theta is equal to 0.1 arcseconds. And that's what we're talking about. And that's a very cool way to visualize our problem as opposed to just having to memorize math. Granted, memorizing math is good, but sometimes they'll put unique twists on the problem, which kind of make a lot of your math a bit more difficult. So visualizing problems is always very good, especially for beginners in Science Olympiad. And something that I'd highly recommend because that's something that I didn't start off doing. And I kind of had to learn the hard way when I was starting off in middle school with astronomy and reach for the stars in that case. So, so this is a very good example of how you visualize that math. So it makes sense, 0.1 divided by 5 years, if that just means 0.02 arcseconds per year. And now the third question is asking us, what is a star's tangential velocity in kilometers per second? There are 206,265 arcseconds in a radian. Now, most people can just sort of use a method of, I'm not sure if anyone's familiar with the train track method. That's something that you learn in chemistry in terms of converting from grams to moles. But so that's something that you can very much do here to convert between units. However, it's very important to understand where a lot of these things come from. And so looking here, looking at this angle and looking at the distance that you moved, you have a lot more context for how you can apply this problem. So I'm not really going to show you how you do it here, but essentially what you want to do is determine what we're going to call omega, which is the angular velocity. In meters per second. This is in meters per second. Well, you want this in kilometers per second, so we're going to make it in kilometers per second. Sorry, this is going to be in radians per second, and then we're going to get our velocity. I got that. And then we're going to make our velocity, v, is equal in kilometers per second. And we know a very cool relationship also that omega times r, which is our radius, or in this case d, so we're going to call this d, times our distance is equal to our velocity. And you can go ahead and use that relationship there. All you need to do is essentially to change, okay, see what this relationship is, see what our angular velocity is, and convert it to radians per second, and then solve our problem. So we know it's 0.02 arcseconds. So I'm just going to mark this with these two per year, 1 year. Well, all we need to do is multiply this by, well, there are 206,265 arcseconds in 1 radian. So we're going to do 1 arcsecond. And then we're going to do, sorry, we're going to do, here we're going to do 206,265 minutes, 1 radian. That's going to convert it to radians for us. And then what we're going to go ahead and do is say, well, this is obviously, this is obviously in years. So to get it to seconds, all we need to do is, well, there are 365 days in a year. There are 24 hours in a day. There are 60 minutes in an hour and 60 seconds there's 60 minutes in an hour and then 60 seconds in a minute. And that will go ahead and give us our omega in radians per second. Then you just go ahead and plug it into here. You already have d, right? You have that relationship already. And if you wanted to make sure that it's in kilometers, all you need to do is go ahead and you already have your definition from what we discussed earlier, parsecs in terms of meters. In this case, it would be this number times this number divided by 10 to the power of 3 because you want it in kilometers as opposed to meters. And you just multiply all that together and you'd get your answer, which if someone's following along at home, which I doubt, but just in case, should be about 8.58 kilometers per second. And that's going to be your answer for part C. I was going to discuss D a bit more thoroughly, but Jeff did a great job talking about the ladder that we use in cosmology and in astronomy, which is essentially saying the farther away you get from much of anything, the different methods you're going to use. Parallax is very low on this ladder. It's something that you use, as Jeff discussed, when you're very close to an object. Generally speaking, this distance is not very large. This is a relatively large angle, but once you get objects that are farther and farther away, you're going to get things that are almost infinitesimally small. You're talking about something like 10 to the power of negative 10 arcseconds, which if you think about it, that's insanely small. That is, like 10 to the power, that is that is 10 millionth times smaller than 1/3600th of a degree. That is an insanely small measurement. And so that's just not going to cut it. And so you're going to have to use a different method that is going to give you a more accurate reading for a distance that's not parallax. Because once you get to units that are that small, you just need to use something like, for example, a standard candle, less something like a Cepheid variable star, or as we'll discuss in a second, our Lyrae stars. So that's just a good way to visualize the mathematics that you use in this event. So I'm going to go ahead and scroll down and talk about a few other concepts. So one of the things that I recommend, I'm actually going to jump down here to this calculator. You might see that I have my trusty TI-84 plus CE as well. You could use really any TI-84 model. Just one of the things that I wanted to talk about is something that I think is very, very important, which is storing numbers that are very common. So a very common number that I come up with as a student, now as a physics student, as well as just something that I came up with a lot in astronomy and science Olympiad, is the gravitational constant. I'm not talking about the lowercase g equals 9.81 meters per second. Meters per second squared. I'm talking about the big G, capital G, that you use in orbital mechanics, which is to say that the force of object 1 on object 2 is equal to G times the mass of object 1 times the mass of object 2 divided by the radius, which is the distance between them squared. Radius is actually a vector, so I guess I should do that, but you don't have to worry about vector mechanics yet. Oh, the days. So this is a big, I think I heard Jeff laugh there. Those are the days, those are the good times of not having to worry about these complex numbers and what vectors mean. But beyond that, we're talking about G, which is defined as 6.67 times 10 to the power of negative 11. Some units, I forgot what the units are. You can solve for the units here if you want. I'm not gonna make that. I'm pretty sure it's kilogram to the negative 2 times meters cubed, and then times, I think it's like per second something. I'm sorry, I forgot the units. I'm a failure in life. But there are specific units for it. But what you have to worry about in these problems is not necessarily units, but the number, because your answer is going to be in newtons. So this should be this number is very important to save. And so the way you can do it is simply, I'm going to go ahead and turn on my calculator. So you press the on button. I should use a different color here. I'm going to use red. Red's got color. I'm going to press turn it on. Then you can go to, let's say I'm going to type in this number. So I just use the D-pad, say 6.67 times 10 raised to the power of, and then you're going to press this key, negative 11, and then type in 11. There, now I have a number. I'm going to hit enter. And then once I hit enter, I can go ahead and save it. All I have to do is click store. And then the cool thing I can do is I can store it as any one of these green numbers, which is very, very useful. So if it's G, capital G gravitational constant, I'm going to go ahead and save it as G. And all I have to do is say alpha G and then enter. That way, instead of having to enter 6.67 times 10 to the power of negative 11, every time you do this math, you just enter G. And on your answer sheet, if you're filling out your answer sheet with your math, all you necessarily have to do, that's not, oh boy, they're asking me something. So instead of having to write 6.67, I can just write G, M1, M2. And then in my calculator, I can also write G times whatever mass 1 is times whatever mass 2 is divided by my radius. Another good thing to save might be a conversion. For example, I could say, okay, I know that 1 parsec is equal to 206,265 AU. That's a very important unit. Maybe I want the definition of a parsec in meters. That might be a good thing to save. And you can save all of these factors in here. And another thing that I have that I take in with me to astronomy is actually I have a sticker inside of my calculator that just has the letters, or maybe you have it on your note sheet since that's I know I'm not sure if writing on your calculators is very within the confines of the rules, but you might want to write, oh, okay, I saved, okay, in G, I wrote gravitational constant. As P, I wrote the conversion from AU to parsecs, right? You have all of that information and you don't have to be constantly jumping back and forth. As well as another thing that I recommend is a reference sheet for all of these conversions, because as fun as it is to derive these answers, if they ask you to casually convert from parsecs to meters or kilometers, or maybe they ask you to convert from minutes to radians, and that's not very fun. Or maybe they ask you for some cool facts like surface temperature of the sun, or maybe the luminosity of an RR Lyrae star. This is going to be a lot more difficult to come by than it would be to just, write it down. It's a lot easier to write stuff down than it is to derive stuff. So I definitely recommend doing that as opposed to jumping through many, many hoops and not finishing your test in time. Again, a lot of the tests this year are based on A, critical thinking skills, and B, having a whole lot of questions. That way, if someone finishes every single question on a test, and it's a test that has 150 different questions that are all relatively hard, then, well, that's going to be a bit more difficult to get all the answers on. And so we'll definitely be suspicious of someone that finishes all of the tests and then gets like 98% of it right. So those are our ways for phasing out cheaters. But that doesn't mean that you should not be prepared as a student and as a competitor. Oh boy. All right. So that's all the stuff that I wanted to discuss. I could go ahead and derive how to get 1 radian from how to convert from arc seconds to radians, but it looks like we're running a bit short on time. We're about 5 minutes out from the time we're supposed to be done. So if anyone has any questions that you want to ask us, possibly on concepts. Well, actually, this is one last thing I wanted to go over. I wanted to talk about as well. There are some units of surface temperature that we wanted to derive, but that is again something that Jeff went over. Responsible as he is, he was able to do a lot better job. He also had a better diagram. I don't know what this rainbow is. I think I might go ahead and replace this rainbow with something a lot more fitting. Let's see, let's go to my emojis and replace it with better rainbows. I think these rainbows are a bit better. There we go. Perfect. So yeah, that looks better. So if anyone has any questions that they like to ask us, whether it's about things that we've done, I know I, for one, am interested in the kind of research and work Jeff does at NASA, or maybe if you have questions about this event, go ahead and drop them in the, go ahead and drop them now, and we can go ahead and answer them. Otherwise, you can go ahead and contact us by probably just messaging this account, or by any means, if you can find us on social media. We're not very hard to look up. So thank you, everyone, and we'll give us a couple seconds for any questions. Balmer lines. Jeff, do you want to go ahead and answer that one? Because I know you talked a bit about them in your presentation.
Yeah, what was I'm not looking at the YouTube. That's why I was wondering.
Oh yeah, it's in the Instagram. I'll go ahead and read you the question. I'm confused about Balmer, Peschel, Lyman lines. I'll go ahead and type the question in the chat. That way, in case I mispronounce something, it's not my head. So. Oh, there we go. I was confused about that too. I was like, isn't it Pashan?
Yeah. Pashan, yeah.
All right, here I sent it in the chat.
Yeah,
it's supposed to be Lyman, not Layman.
So Pashan and Lyman lines have to do with if you have the atom and you have the various atomic energy orbitals. This has mainly to do with hydrogen and helium. Basically, complex. So I guess I'll do my best to draw it out. So you have the nucleus here, right? And then you have the various, I'll just make it like this. Energy level 1, this is the ground state. This is kind of like where all the electrons kind of, settle. It kind of originates there. It's kind of like that. And then you have energy level 1, 2, 3, all the way up to where the electron ionizes. So electrons can absorb a photon, and the Lyman and Paschen lines all have to do with where it starts. I'm not exactly sure which one it is, but it's like I want to say Lyman is the first level all the way up. Paschen is
Yeah, I think
n
Passion's
equals
the
2.
third level. I think Lyman is 1, Balmer's 2, and then Passion is 3.
Yeah, thanks for that. Yeah.
Yeah. I think, and I say here, this is kind of me cheating, looking at I have a few diagrams here, but essentially, I think that all I was ever asked about the event is the difference between Balmer and Passion, and then just the Lyman series. And the difference is that just you end up Balmer and Passion are jumping between excited states, and then Lyman series is jumping to a ground state. It's grounding whatever you have.
Right. Yeah.
That generally leads
Something
to
like that.
generally you're going to emit something in the visible spectrum if you're in the Balmer series, as well as a bit of the Lyman series. But Passion series, you're going to have a bit more high energy emissions there.
Yes.
There's actually something that I recommend is I guess it's kind of cheating, but you can access what's it called? I swear, OpenCourseWare, MIT OpenCourseWare. We actually did a unit talking about how you can derive the wavelength of the wavelength that's emitted based on which orbitals you jump between, and you can define, whether it's going to end up as IR, as visible, as ultraviolet. You can define the wavelength of your of your wave, and that was like the last unit that we did in our physics class. So if you want to go ahead and check out 801 OpenCourseWare, that might definitely be helpful. It's a bit advanced, and I highly doubt you get questions on it. But obviously, if you're asking questions on it, that means you got a question about it. So I stand corrected.
If someone's crazy enough, which could come up, who knows?
Yeah. All right, my eyes are on the chat to see if we get any more questions, but if not, then I hope everyone has a fantastic evening and a great weekend. And for any college students who have finals coming up, I wish you the best of luck. And any competitors who are going to any competitions like Solvi or Yosemite next weekend, I wish you the best of luck as well.